Okay, the torsion today's class we are going to discuss torsion. So if I take this pen and rotate this in this direction and the other in at opposite direction, the pen will be twisted, experience a opposite moment at the both ends. So the torsion is twist or torsional moment. Okay, so let me give you some example. So example 1, in this example say a member, this end is rotate clockwise and the other end is rotate counterclockwise. Because of that, this member is subject to a twist. Now consider another example. A shaft is attached with a bearing, and this is my shaft, and this is a bearing. Okay, now this shaft is rotating in this direction, and the bearing will try to oppose this rotation bearing will try to oppose this rotation. As a result, this shaft is this shaft experiences a twist. And the third example I'm trying to give is so consider a turbine generator assembly. So this turbine is coupling with this generator, and there is a shaft which has two couple A and couple B. Now when this turbine rotates, the this rotation is transferred to this generator by the shaft AB, A to B. And as you see, the torque here is this coupling is experience a torque, and this is opposite. Similarly, this one is clockwise, but because of and this shaft experience torque at one end is anti-clockwise and the other end the clockwise. So as a result, this AB shaft experiences twist. Now so these are the three examples I gave, and the torsion is very important for designing your setup. in this particular case, you need to figure it out how much torsion will generate because of this power transmission from turbine to the generator, and and we can actually calculate how much stress is developed because of this torque. Now let's consider a case. Say uh, this is a shaft, and this shaft is, this end is fixed. Okay, now if I draw a line here, if I draw a line here on the surface of the shaft, and then the same shaft experience a twist, this torque is applied. Now this line is going to shift here. This is the previous line, and this is the new line. Okay, so this is an example where you can see a cable. There is a white rectangular mark here. If this cable is experiences torque, and the left front picture is a before torsion. This white rectangle is now changes, is no more a rectangle, because this cable is experience a torsion. So um, if a member this is a member BA, and there is a plane and now if member AB I cut at the say center, now this piece is BC, and this one, if I enlarge this, and these are elements on the surface of the C end. So these elements experience a force called df, and from the center to this element the distance is rho. Okay, now the torque is moment. The torque is a moment, and this, as you know, for the moment m, how can we calculate the moment? Moment we can calculate by force into force multiplied by distance. Now similarly for the moment, for the torque, we can determine by force and distance. Now in this particular case where df, force is df, and the torque dt is df, which is elemental force multiplied by this distance, this distance. Now for the entire area we can find the torque dt, integrate, you get df rho, which we can write rho df. Okay. From the in our previous chapters we learned that force equal to stress multiplied by area, right? Or we said stress equal to force divided by area. So the torsion, I will show you later, with the torsion the shaft experiences shear stress, so stress equal to F by area. We can say F is equal to tau multiplied A, and this, if it is elemental small quantity, we can write tau dA. We can say if dt we integrate t equal to rho tau dA. This is my equation 1. Okay. So we will come back to these equations later. Now let's consider a shaft which is fixed at one end and which length is L, and this shaft is subject to a torsion. Okay, and this is a line, and this line change to this line, because when this rotates, when we apply torque here, this line changes to that line. So this is an angle gamma, and this distance we call rho, and this angle we call it phi. Phi is angle of twist. So let me say it again. So this beam A, B, we apply torque, and because of this torque, this shaft actually twists, and the twist of angle is phi. Now, if you remember from our previous lectures, we said when we apply stress, if we apply shear forces here, okay, apply shear forces, these change to this body actually deform, and this angle is called shear strain. Similarly, in this circular shaft, when it's subject to twist or torsion, it experiences shear strain, and this shear strain we can define this shear strain by the shear strain gamma equal to rho phi L. Now there's one information I want to give here. Couple of this phi angle of twist is proportional to torque. That means if your torque is more, this angle of twist is more, and this is also proportional to the length, this length of the shaft. Okay. Now, so this is my equation 2. Now this gamma is maximum at this alpha, the shear strain is maximum at rho equal to C, by means basically this distance from, so the rho is actually all the point here. So let me explain the rho and see. The rho means all the distance here, all the distance here. This is a point, this is a point, this is a point, this is another point. But the C here, the from center to the surface, to the boundary, this is C. So the strain will be maximum at the outer surface, and this outer surface, the radius is C. So we can say rho maximum equal to C phi L. This is my equation 3. Now from 2, I can say twist angle phi is equal to L gamma shear strain by rho, and this is my equation number 4. And if we combine 3 and 4, I can write sigma max equal to C by L multiplied by L gamma rho. Sigma max equal to C gamma by rho. We can cancel out L. To rearrange these, shear strain equal to rho by C multiplied by maximum shear strain. Shear strain, this is my equation 5. Now Hooke's law, we know that for the Hooke's law there are normal stress sigma is equal to Young's modulus multiplied by epsilon, and if it is shear stress, we we can write shear stress is multiplied by G bar multiplied by shear strain. So here, so this is my equation number 6. This is my shear strain, and this is modulus of rigidity. So multiply both sides of equation 5 by modulus of rigidity G. We can write that G gamma is equal to rho C G gamma max. Now from 6, this is my equation number 7. From 6 and 7, if I replace G gamma with the shear stress, I can write tau equal to rho C tau max. So here I replaced tau is equal to G gamma with the, G gamma with the tau, and G gamma, similarly G gamma maximum also tau maximum. Sorry, G gamma tau maximum. So this is my equation number 8. So here, so your maximum stress occurs when your strain is maximum. I'm saying again, your maximum stress occurs when your strain is maximum. So we can replace G gamma maximum with tau maximum. Now let's recall the equation number 1. Remember the equation number 1, we said torque equal to integration of rho pi dA, and so recall equation 1, which is T equal to rho tau dA. So T, we can write rho, and from the equation 8, we know that tau is equal to rho by C multiplied by tau max, rho C tau max. So here rho square there's a dA here, rho square 1 by c tau max dA. Okay. Now, so I want to rearrange this equation T rho square c tau max dA. And we can bring, because rho square, can bring tau max by divided by c rho square dA. This particular integral is, this is polar moment of inertia of the cross section with respect to its center. And this polar moment of inertia we can define, we can simplify this, we call J. So J is rho square dA. Now, so we can write this equation T is equal to tau max C J. If we rearrange, we can say tau max equal to TCJ. So this is the equation of a stress on a shaft which experience a torsion T. Now, if we combine the equation 8 and equation 9, we can write tau is equal to rho c. If we just plug tau max at equation 8, going to give us Tc divided by J. Okay. And so tau equal to rho T by J.